All right, let's talk about the Brayton cycle with regeneration. In the previous video, we talked about the open cycle and closed cycle Brayton cycle, and in open cycle open system Brayton cycle, we saw that turbine exhaust is leaving to the environment, right? So instead of leaving to that environment, what we are doing that in this Brayton cycle with regeneration system, we are taking that exhaust, right? We are taking that exhaust and then bringing that exhaust in a system. That's in that system, basically that exhaust of the turbine is rejecting the heat, right? By utilizing the heat, we will heat it up the compressor outlet or the compressor output, right? So if we heated up the compressor output or preheat that air or compressed gas, then basically we'll have preheated gas in the combustion chamber. And eventually, if we preheat the combustion chamber, if we preheat the combustion chamber input, then what will gonna happen that the temperature of the combustion chamber exit will be sufficiently high to increase the turbine efficiency, right? Because our goal is to increase the inlet temperature of the turbine is high, so that we can have maximum uh, work output from the turbine. So that's the goal of the Brayton cycle of the regeneration. So let's go ahead and draw the diagram of the TS diagram of this regeneration cycle. So if we draw the regeneration cycle TS diagram, it will gonna look like so T. So we can see from just by looking at this diagram that maximum temperature of this cycle will be at point 3, because this is the combustion output, right? So it will be like maximum temperature, and the minimum temperature of this system will be fresh air, right, at point 1. So let's start from the point 1. So what is happening in the point 1 to 2? So process 1 to 2, basically it's isentropic compression, right? Compressor is compressing the gas 1, and this is 2. Excuse me. So from excuse me. So from 2 to 3, we can see that multiple thing is happening, right? So from 2 to 5 and 5 to 3, but let's imagine that there is no regeneration unit. Then what will gonna happen? So it will gonna go to straight 2 to 3, right? And then from 3 to 4, it's expanding, right? In the turbine, so that's expanding and temperature is falling. And then from 4 to 6, it's rejecting basically the heat, right? And then if we consider this again from 6 to 1, basically that to complete the cycle, then it will gonna look like this, right? Now what is happening in between 2 to 3 is that regenerator is rejecting the heat, and that heat is absorbed by the compressor output, right? So thus the temperature is increasing, and then it's going to the point 5, right? So it will be 3, it will be 4 and 6, right? And then yeah, so this is the TS diagram. So what is happening here, basically 2 to 5, this portion is heat Q regeneration, right? Regen. And then from 5 to 3, this is basically for combustion, right, which is Q in, right? And then from 6 to 1, basically it's releasing the heat. That means here it's Q out. And from 4 to 6, basically this much of heat is saved, right? So this 4 to 6, that much of heat is absorbing by this by this the compressor inlet, right? So basically this would be Q saved or recovered, or Q recovered, or you can write it whatever you think. It's Q generation, right? Q regeneration. So that's the TS diagram of this system, right? So if we want to determine that what is the regeneration of this cycle, right? So we can write it excuse me, Q regeneration actual is equals to actually, if it is ideal cycle, right? In actual cases we see this one, but in ideal cycle it will increase, the temperature will increase more. So in that case it will be actually ideal case it be something somehow like this, and then 5 prime and this is 5 prime. So I think it will be a little bit changed. Here, so this is 4, this is 5. Okay, all right. So the Q generation actual would be H5, excuse me, H5 minus H2, right? And then Q generation or regeneration of this cycle, maximum Q regeneration, maximum, which is equals to this one is H5 prime, right? 5 prime point minus H2. So H5 prime, which is nothing but H4, we can see that at the same point H4 minus H2. So now there is a term for this turbine. So we know the efficiency of the Brayton cycle, right? In Brayton cycle gas turbine. However, since we are using this unit, right, regenerator unit, this portion, we have to determine that how much heating is generating from this unit, right? So to quantify that generation, we use a term, it's called effectiveness. So that effectiveness expressed by epsilon, right? So that epsilon equals to Q regeneration actual versus Q regeneration maximum, right? So actual, we know that H5 minus H2, and the maximum we saw that H5 prime minus H4, it will be H4 minus H2. So by considering the cold air assumption, we can write that epsilon equals to T5 minus T2 and T4 equals to T4 minus T2. So that's the expression of that effectiveness. So basically, what are the things you are looking for? You are looking for the T5, T4 and T2. Basically that the compressor output, and then turbine output, and the regenerator output, or the combustion chamber input, whatever, I mean, either way, right? So if we know this temperature of this 3 point, then we can determine the effectiveness of that regenerator. And then the efficiency expression of that regenerated cycle, right? Thermal efficiency of that regenerator cycle will be 1 minus T1 divided by T3 times RP, pressure ratio, power, K minus 1 divided by K. So this is the expression for efficiency. So now we know that effectiveness of a generator and efficiency of the generator of a Brayton cycle, right? Modified Brayton cycle. What other things that we can moderate or we can change in the Brayton cycle? So we can do multiple things, right? So to increase the efficiency of this cycle, what we have to do is that increase the work output and decrease the work input or work consumption, right? So in that way we can increase the efficiency of this in this system. So so let me draw it. So how we can increase that net work output, right? W net. We have to increase this turbine output and decrease this compressor input, right? Compressor work input. So then we can increase the total or net work output of this system. Eventually it will increase the efficiency of the cycle. So how we can increase the turbine efficiency and how we can how we can increase the turbine work and how we can decrease the compressor work. So there are multiple ways we can do that. So let me give you an example here. So for example, in chapter 7 we know that if this is a PV diagram, right? PV diagram, the compression process, usually we in ideal cases it's an isothermal process, and we can express it like this: 1 2, let's consider 2, right? However, in actual case we see that compression process doesn't follow that actual isothermal path, right? It's a compression process, it's a polytropic path. So this is isothermal and this is a polytropic, not isothermal, polytropic, right? And then we see that this is the ideal case, right? And the area under this curve is work done, right? So and this is, let's say this is 2 prime, right? So the compression work is happening here is that the area under this curve, right? So which is relatively higher for ideal cases, but in actual cases it's still relatively lower compared to this isothermal. Now when we compare with the ideal case, then how we can decrease the work consumption. So let's consider that another ideal case, right? So that ideal case, what it will gonna look like if we do something like this. So first it comes here, right? Compression, and then it cools down, and then again it goes back to this one, right? In that way, if we have some sort of like this the breaker in the path, then how this work consumption is reducing. So now you can see that area under this curve is saved by excuse me, so this will be actual 2 prime, right? So area under this curve actually is saved by this amount, right? So we saved work. So this much of work we saved. So meaning that if we have, instead of direct path, if we have some sort of like intercooling system in the compressor or multi-stage compression system, for example 1 to A, its compressor is working, and then give some rest, and then maybe send it to another compressor, and that compressor is basically, let's say this is B to D, and compressing again from B to D. So that means if we have multi-stage compressor, right, then we can reduce the work consumption. Right? So if we reduce the work consumption, then W net expression of a closed system, we know that or maybe let's focus on the Brayton cycle, the W net equals to W turbine work minus W compressor work. So if this thing goes down, then the efficiency or the total work done by that system will goes up. Or we can do making this constant, right, compressor constant, and goes increase the turbine work output, then we can increase the W net as well. Or we can do both at the same time. We can increase the turbine work output and decrease the compressor work output, and eventually we will be able to increase the net work output. So by that way we can increase the efficiency, right? So that means that if we incorporate multi-stage compression and multi-stage expansion, then we can increase the net work output of the Brayton cycle. How we can do that? So that's the topic 9.10. Basically it's telling us that if we have multi-stage compression, for example compressor 1 and compressor 2, and then if we have multi-stage expansion, then eventually we can increase the net work output of this system. Now the question is that how we can incorporate the multi-stage compression, right? So the compressor outlet, its a temperature is rising as soon as the pressure is rising, right? So that's why we need to implement some sort of intercooler to cool down the temperature at maybe at room temperature, not even room temperature, at least close to the room temperature, right? Because this is, let's say this is room temperature, right? And then we the same exhaust of that compressor 1 will be input of compressor 2, right? And then similarly we implemented two-stage compression here, two-stage compression. And then similarly in the turbine, what we are doing here, we are taking the output of the combustion chamber high temperature gas and then expanding it, and then again we are reheating it, right? After reheating it, and then bring that gas to another turbine to get some additional work. So that means that we are basically decreasing the WC here and increasing WT here, right? So that's the goal of the Brayton cycle with intercooling. So we are implementing intercooling system in between the compressor, and we are implementing the reheating mechanism in between the turbine, and also we are utilizing that regeneration, how the turbine 2 outlet is going to a regenerator, and then we are basically absorbing that heat and then bringing it to the combustion chamber just to preheat, work as a preheater, right? Work as a preheater to the combustor. So then the temperature of this 0.6 and goes really high. So now just by taking just by looking at this cycle, we can see that maximum temperature can be at 2 point. One is that combustor output, right? Another is the reheater output. So these 2 point could be the maximum temperature, and the minimum temperature would be right here at 0.1. So if we draw the diagram, TS diagram of this one, then we will see that we maximize the efficiency, or we can maximize the net work output of this modified Brayton cycle. Now in the exam, I might ask you that to increase the turbine efficiency, or to increase the efficiency or the net work output of the Brayton cycle, what are the criteria, or what should we do? Maybe then I will give you guys this type of diagram, and then ask you the TS diagram, representative TS diagram, right? So the representative TS diagram of this cycle will gonna be, so let's consider from 1 to 2, it's compression, right? So 1 to 2, it's basically it's compressing, right? 1 to 2, this is 2, and then from it's 2 to 3, it's basically it's cooling down the temperature. So if it is a TS diagram, S and T, intercooler is basically reducing the temperature, right? So from 3 to 4, again the temperature is increasing and pressure is increasing. So this is 3 to 4, right? And then 4 to 5, we see that it's absorbing heat from the regenerator, right? So basically it will gonna look like this is 4 to 5. And then from 5 to 6, the combustor, it will experience the maximum heat, which is 6, right? And then from that combustor, it's going to the turbine, and then from the 6 to 7 is turbine 7 is the turbine outlet, right? Expanding. So when it's expanded, it reduce the temperature as well. So this become 7. So now from the 7 to 8, again it's gaining the heat. That means the temperature is increasing. So let me write it here, right? So this is 7, this is 8. So for this cycle, we try to maintain the temperature of 6 and 7 at the same, right? And then from 8 to 9, what is happening? Again, it's expanding and then reducing the temperature. So expanding and reducing the temperature, which is 9, right? Actually, and that temperature is similar to 7, the turbine 1 outlet, right? So this is 9. And then from 9 to excuse me, if we close this one right here, from 9 to 10, it's basically somewhere between here. So this point, and then from 10 to 1 would be this, so 10. So some of the interesting thing here would be that we can see that temperature at 0.5, 7 and 9 are the same. Why? So the temperature outlet of the turbine 1 and turbine 2 is the same, and the 0.5, the temperature is same as 7 and 9, because it's generating or preheating the air just by taking that heat, right? So basically that T9 and T5 is the same, and also the T7. And then T6 and T8 is the maximum temperature of this cycle, because they are the combustor output and reheater output, right? And what else? So 3 and 1 would be the same, because after the combustion, right? So before the compressor, both of the compressor input is the same. So this is compressor 1 and this is compressor 1 and this is compressor 2. And then compressor 2 output temperature and regenerator temperature will be same, right? So actually it would be a little bit modified. Okay, it would be something like this. Okay, so this would be 4. So that's the diagram, TS diagram of this modified cycle. Now if I ask you in the exam or in the quiz that we don't have 2 turbine, okay, we have only 1 turbine, however we have 2 compressor, right? For example, we don't have here reheater, it's just going directly here, right? However, we have 2 stage compressor and 1 stage turbine. Then what would be the TS diagram, right? So let me write 2 stage compressor and 1 turbine. Then what would be W net or the TS diagram, right? TS diagram, or maybe like 1 stage compression and 2 stage expansion, right? Then what would be the diagram, TS diagram, right? So this type of question I might ask in the exam, right? But one thing I would like to mention about this modified Brayton cycle with 2 stage compression and 2 stage expansion, basically that this output, the compressor 1 pressure and compressor 2 pressure output, that means P2 and P4 is the same, and similarly compressor 1 input and compressor 2 input is the same. That means the relation will become something like P2 divided by P1 equals to P4 divided by P3. So this is one relation. And if we look at the turbine, right, similarly if we look at the turbine, pressure at 0.6 and pressure at 0.8 would be the same, because both of them are inlet for those turbine, and then pressure at 7 and pressure at 9 would be the same. So the relationship will be P6 divided by P7 equals to P8 divided by P9. So that's the relationship between the pressure and the temperature. We saw it here. We can see it here that T6, T8 same, T7, T5 and T9 is the same, and T4, T2 and T10 is the same, and T3 and T1 are the same. So that's all about Brayton cycle, modified Brayton cycle. We will do some math problem based on these cycles. So thanks for watching this video, and we'll come back with the math problem.